Welcome back. So I was talking about the SDGs and that massive opportunity. Well, the SDGs represent a massive challenge as well, which is about ecological collapse, about climate change, about things that happen very, very quickly. And we talk about exponential developments here. We're talking about very, very slow, gradual developments first, and then suddenly it changes dramatically. And the same is true for the technology that poses the massive opportunity that we have in solving this crisis and other crises that we have right now. But we need to really deeply understand what exponentials actually are, because we're not built for understanding exponentials. We're trained as humans for, let's say, 70,000 years to think in linear extrapolations. So I want to talk a little bit about some ideas about exponentials. First off, exponentials are anything that doubles in the same amount of time. So when you look for doublings of things, whether that's computational power, or whether that's money, or whether that's customers, or whether that's CO2 molecules in the atmosphere, it doesn't matter. Anything that doubles in a certain amount of time hints towards an exponential growth or decline of something. And this is what we need to be looking for in order to think about it. So this grows extremely, extremely quickly. So usually in an exponential growth, the last 4 steps of the growth happen to incorporate more than 90% of the entire growth of the curve. That is like massive. We have a really hard time imagining that. So for example, a very common example is you take 30 linear steps, which means that usually as a grown human you would walk roughly 30 meters. But if you took 30 exponential steps, that would take you around the globe 28 times. That's hard to fathom. So what I like doing is I have this little image in my mind of how to think about this, and I want to show this to you. So I'm going to draw this up for you quickly. So this is a typical exponential curve, and the horizontal lines, the vertical lines, they represent time frames. Let's say every 10 years. So with every 10 years, there's a massive growth. And let's look at the increase in this time frame here. So we have an increase of whatever potential that was. Let's say computational power of that's a radius, and we can say this was our potential, the added potential in this time frame. Now let's forward another 10 years, and now we have a radius of this, which means that our potential now is about that size. And if we forward another 10 years, our radius is now like that, and it doesn't even fit anymore. It's like massive, right? So this is what happens with compute, for example, at the moment. And there's an interesting second thing that I'd like to talk about in that respect, because very often we hear that the growth of compute in the way we're doing it right now has come to an end. But if you look at computational power, beginning with Ada Lovelace and Charles Babbage building mechanical computers, we went through several technologies, which means that we're constantly building new technologies on top of each other, and we call that stacked S-curves. So we're going through mechanical computing, we're going through tubes, and then we go to transistors, and now we're going into the next step. And this is why this is how we think about real exponential growth. It's multiple developments stacking on top of each other and feeding off each other. So now there's a second interesting thing that happens, which is based on that stacked S-curve phenomenon. I call it the expert delusion. Whenever you ask an expert, it doesn't matter where you are on your exponential curve at the moment, but whenever you ask an expert, how's it going to continue? The expert will tell you that it's a linear extrapolation. And what that looks like is like so. So you ask an expert, how's it going to continue at this point in time? And the expert will tell you it's going to be linear. And then a year later, you're going to ask the expert, how's it going to continue? And the expert will tell you it's going to continue like this. So why do they do this? It's very simple, because they are locked into the current paradigm of doing things. So they're locked into the mechanical part of compute, or they're locked in the tube part, or in the transistor part. And that's why they cannot imagine an XS curve that will add to the exponential curve. And why they don't take it seriously for a while is because of what I call the linear superiority illusion. So what does that mean? When you, for a long time in an exponential growth curve, it underpromises. It doesn't look very exciting. It looks less exciting than your linear projection. But then suddenly it breaks through your linear projection, and that's when it becomes more powerful. And these are some of the concepts that we need to have in mind when we think about exponentials and exponential growth and decline in technological terms, in societal terms, and in environmental terms. Okay, thank you for now.